Thank you all for being here today. So I'm sure by now we're all familiar with the steps we need to take to limit warming, and reducing our emissions plays a huge part in this. But like Corey said, what if I told you there was also another solution, another way to achieve our net zero goals? Not to totally undermine the importance of reducing our emissions, that will always play a huge part in this. But there's been this new idea that's been around for quite a while, actually, but it's only just starting to be taken seriously as a potential climate solution. This idea is known as carbon dioxide removal, or CDR for short. CDR aims to deliberately capture CO2 from the atmosphere and durably store it for long period timescales. The state of California has actually legally committed to achieving net zero and negative emission goals by utilizing CDR technology alongside traditional emissions reduction strategies. But little steps have been taken to scale CDR to the extent it would need to be scaled in order to have an impact. And this isn't just in California. All over the world, people have begun recognizing the need to reach not only net zero goals, but also net negative goals, which means that we extract more CO2 from the atmosphere than we emit. And I want to emphasize that the goal behind this project is not to endorse CDR, but rather to evaluate its potential as a supplemental strategy to limit warming. So there are a ton of different CDR strategies. There are more engineered focused strategies, there are land-based and ocean-based strategies, and the one that we're going to chat about today is based on the idea of enhanced weathering. This builds on the foundation of rock weathering, which is a natural geological process that sequesters CO2 as rocks dissolve over long period timescales. So when rocks are weathered by rain, they can actually dissolve and capture CO2 in that dissolution process. That CO2 gets converted to bicarbonate, which essentially traps the carbon in a stable form, so it can't be released back into the atmosphere. Over time, bicarbonate can make its way to rivers and to the ocean, where it remains for thousands of years. So enhanced weathering tries to speed up this process by spreading crushed up rocks or minerals on surfaces like farmland, for example. And because they're so crushed up into finer grains, they dissolve much more quickly, thus can capture CO2 more efficiently and convert that to bicarbonate. But what if we sped up this process even further and we brought these crushed up minerals straight to coastlines where they could rapidly dissolve into the ocean via wave action? This brings us to coastal enhanced weathering, which is essentially enhanced weathering, but at the beach. And the idea is you can actually just see how it's depicted in this image. It's sort of this like bluish greenish pigment on the sand. This is actually olivine. That's a silicate mineral that's been deposited in the sand. Olivine's been used in 2 coastal enhanced weathering projects on the East Coast, one in New York and one in North Carolina that are actively going on right now. And the idea is you deposit these certain kinds of minerals, sometimes it's olivine, and over time, they're washed into the surface of the ocean via wave action, and they dissolve. And this dissolution increases the alkalinity of the ocean, but also it increases the ocean's capacity to absorb atmospheric CO2 as bicarbonate in the ocean. So how this works is typically CO2 in the ocean and CO2 in the atmosphere are in this equilibrium. But when these minerals are introduced into the marine environment, the dissolution of these minerals causes CO2 in the ocean to rapidly convert to bicarbonate. So with less CO2 in the ocean relative to the atmosphere, naturally atmospheric CO2 is drawn into the ocean to try and balance out this equilibrium again. And as long as these minerals remain present in the marine environment, the cycle can continue, where atmospheric CO2 is drawn into the ocean, converted to bicarbonate, and so on. The cycle continues. So in theory, this could be an excellent CDR strategy that we could potentially scale all along the California coast. And it's also something we could easily integrate into the hundreds of active beach nourishment projects that exist in California. But we also have to acknowledge that this carbon removal process is extremely hard to measure and complex, making it difficult to identify where along the coast this could best work. Where can we get the most CO2 drawdown? There are also a ton of regulatory barriers in California that, in terms of intervention into the marine environment, and for good reason, but how do we go about permitting this? Because there isn't a designated agency or environmental law that's really capable of governing CDR right now. So how do we regulate these kinds of interventions? So recognizing this, my team and I built our little suitability map that I'll show you guys in a second. This is an interactive map of the California coast, and it scores segments of the coast based on their suitability for deploying these coastal enhanced weathering projects. And I want to emphasize that it scores segments relative to each other. It doesn't provide any sort of absolute value of this segment can sequester X amount of carbon. So the way we did create this scoring was based off of a two-tier framework. So tier 1 looks at implementation feasibility for things like permitting. So if a segment would require an intense, strenuous permitting pathway, it's just deemed ineligible for the sake of efficiency. And tier 2 looks at the relevant oceanographic drivers that influence carbon removal processes along the coast. So getting into tier 1, this is our eligibility check. Obvious must-have, the segment must have a sandy beach that's compatible with nourishment infrastructure for physically depositing the grains. And then we get into some hard flags. So the segment can't be inside a no-take marine protected area due to permitting complications. Eelgrass and kelp canopy proximity are also relevant here, but in different ways. Eelgrass beds are actually designated essential fish habitat, so any interventions into this environment would likely cause a lot of permitting complications. And kelp is actually super sensitive to changes in local ocean chemistry. So any spikes in alkalinity, which is essentially what we're trying to do, would potentially disrupt this habitat. So we don't know the specifics yet. So overall, it's just best to avoid these areas for now. And then we added a little soft flag here. Ideally, the segment isn't any sort of critical habitat for any endangered species, just to stay on the safe side. But it turns out a majority of the California coast is some sort of designated critical habitat. So we really can't make this a hard flag at the moment. But also, there have been no studies that have shown that these mineral amendments do cause harm to the marine environment. So we're going to play a little video here. This is getting into, oh, the lights are dimming. We're going to get into our suitability map here. This is tier 1, so this looks at eligibility. And you can see the segments highlighted from red to green. Red is ineligible, green is eligible. And we're going to zoom in on a section of the coast here that we all should know very well. This is San Diego. And we can hover over a segment and we can select that segment. And this white panel pops up with the eligibility status and the reasoning as to why it's eligible or ineligible. And the fun part is you can actually overlay a ton of data sets onto the map. So just taking into account things like marine protected areas and nearby critical habitat, that's what's being showed right now. And we can also factor in ecological considerations. So eelgrass beds, eelgrass is super prevalent in the San Diego region. And we can also overlay kelp canopy onto the map, which is super neat. And so overall, the map in tier 1 just gives us a better understanding and inventory of some of the regulatory considerations that would go into evaluating a segment for a coastal enhanced weathering project. So if a segment ideally passes all of these checks, it can move on to tier 2, which is the actual scoring part. This evaluates the relevant oceanographic conditions that are relevant to the carbon removal process. So this suitability metric is solely based on physical drivers because it turns out that CO2 storage efficiency is very dependent on where you are on the coast because of all the relevant oceanographic drivers influencing the marine environment, thus influencing carbon removal potential. So recognizing this, we gathered the relevant oceanographic data, and we used this data to evaluate the 4 phases of this carbon removal process. And the 4 phases or 4 subscores are broken down into dissolution, residence time, efficiency, and storage. So dissolution looks at how fast the minerals are dissolving in the ocean. Residence time looks at how long the grains have to remain in the surf zone where they're able to dissolve. Efficiency looks at once the minerals have dissolved and the water does increase in alkalinity, how much CO2 can actually be drawn into the ocean. And then storage looks at, well, what happens if the water becomes too alkaline? This could trigger something called calcium carbonate precipitation, which could essentially reverse the carbon removal process. And these are the relevant oceanographic drivers that make up each phase or each subscore. And since there's no standard way to measure this specific coastal carbon removal process yet, I gave equal weights to each driver, meaning that all of these metrics are weighed equally in terms of how much they would influence their respective subscore or phase. In reality, certain drivers will likely have more influence than others, but we just don't know the specifics of this yet to make any sort of assumptions. So this is a first step in evaluating that process. So we're going to go back into our map here. So it's highlighted in eligibility. We're going to switch to the suitability tier 2 score. So you can see now all of the eligible segments are highlighted from dark green to yellow. And we're going to zoom in on a section of the coast that scored super well. This is a little cluster in Santa Cruz. So you can click on an eligible segment. It'll tell you the exact location and the composite score. And what's super neat about this is you can click on a subscore. It has a little drop-down button, and it gives you a brief description of the process and how this is relevant for carbon removal. But it also gives you those exact oceanographic metrics for that location. So all of those scores factor into the dissolution score, which factors into the overall composite suitability score. But you can see this for every single subscore or phase. You can see this for residence time, efficiency, and storage. All of that data is the exact data at that location. That feeds into the composite suitability score. I want to highlight closest mineral source. That's something I don't have too much time to get into now, but ask me again at the end. And we also have the regulatory flags here to consider. This segment is critical habitat for a few listed species, so we want to be cognizant of that. And also kelp canopy proximity and eelgrass proximity is still relevant here. But I want to zoom out a bit and go down along the coast to a section that didn't score as well as Santa Cruz did. This is a section in Malibu, so you can click the segment, it'll tell you that location and the composite score, which is pretty poor in comparison to Santa Cruz, likely due to the lack of wave energy here. You can see that's 0.6. And the storage, the sea surface temperature is a bit on the warmer side, which isn't super ideal for carbon removal. But overall, the tier 2 suitability phase of the map, it's just super efficient to have all this data and all these suitability scores in one place to better understand why certain sites perform better than others, to base our decisions on the best available science. So moving on, to address some of the limitations of this project, this is obviously still a very new, active area of research, so we don't know how much influence certain drivers have over others. And also, coastal zone and surf zone observations are pretty limited along the whole coast of California. So some of the measurements that we have take measurements that are a few kilometers offshore, so they're unable to capture the exact surf zone dynamics. So that's something to flag. And also, this framework omits some relevant non-physical dimensions of suitability, so like community consent and politics and grain size and transportation and fisheries input and so many more relevant considerations that are just beyond the scope of this project at the moment. So some next steps. If we want to do CDR or coastal enhanced weathering right, we really need the infrastructure to do so. So we need streamlined permitting. There are too many barriers to entry because our permitting system just isn't really set up to regulate these types of interventions yet. So having a consistent, streamlined pathway would greatly reduce that burden. We need standardized MRV protocols, so measuring, reporting, and verifying that this carbon removal process can actually do what it's saying it can and remove carbon from the atmosphere. And community outreach and coordination with fisheries, that is super, super key here. The last thing we want to do is exclude the people that live at the coast and work at the coast from these kinds of decisions. And of course, pilot projects doing these experiments in the coastal ocean and in the surf zone to get the most accurate data measurements possible. There are so many research institutions in California, like Scripps, that have the capacity to perform pilot projects like this. It's just a matter of getting started. So wrapping up here again, I'm not trying to endorse CDR or coastal enhanced weathering specifically, but there could be a lot of untapped potential here in terms of carbon removal capabilities. But the only way we can do this is if we do this right, which means being 100% certain of the impacts and the outcomes associated. This project is a first step in that process. And I want to take the time to say some thank yous to my incredible, incredible cohort. I couldn't have done this without you all. To my my legendary capstone committee, Mark Merrifield and Connor Mack, especially Connor Mack. He's been such a mentor for me these past years. I truly wouldn't be here without him. To Jada Ryan and Corey Gabriel for making CSP such a safe and supportive environment to really explore my true passions. And to my friends and family for being here today. My family's here all the way from Gaithersburg, Maryland. Shout out to them. But thank you all so much for your attention. I'm so honored to have this platform to share my research with all of you. It truly means the world to me, and I hope you enjoyed. I'll take questions now.
Yeah, Thank you so much, Ella. That was really an incredible presentation. I am wondering a little bit about, you mentioned that there isn't any research saying that this could be a harmful process. I am wondering whether or not there's any research showing how it could actually benefit even particularly endangered species. I'm thinking specifically about that drop down that you showed was about abalone. So mollusks need this bicarbonate in order to exist, and ocean acidification is just getting worse. So is there any data that you've found that actually suggests that this could be beneficial to endangered animals?
So
thank you.
My research mainly looks into how this could counter ocean acidification. It didn't go into the specifics of what kinds of animals this could benefit or harm, but that's something me and Naomi talked a lot about at a conference we got to attend. Thank you to Julia Brown for sponsoring that. But mainly the studies, we talked about the Northwest Pacific, especially like the Salish Sea. So doing these types of open ocean alkalinity enhancement projects, not specifically coastal enhanced weathering, but just dumping alkaline minerals, like usually dissolved alkalinity, into the water. That is actively going on right now at Woods Hole, I think. So looking at how those could raise alkalinity levels, we don't know how those could impact, the species that live there yet, but it's definitely an active area of research looking at it to counter ocean acidification.